the Bootstrap compiler for base code, which is written in C++. But first, had a follower ask about a program they're trying to write in C++, and this is kind of a common issue, believe it or not. So I thought I would take this program they're trying to write and I would write it here on stream to kind of give an example of how you might tackle this issue. So what the program does is compute change. So you're given an input amount, there's a price, right, for whatever you're buying, and then we're going to compute what's owed to you, and then I think the intention of the example program is just to break it down into the constituent pieces, it looks like. So this is for motorcade. Was the idea that you were trying to generate, so I don't know if people do this in other parts of the world. In the US, if we go to a store and we buy something with cash, so say the item is $5, that's what it cost, and you give the cashier a 20, then the cashier, if they're old enough, the youngins don't do this so much, they'll just kind of drop the change in your hand. But we old fogies would give you a 10, or actually we'd give you a 5. So we'd say 5 is 10 and 10 is 20, right? So we give you a 5 and a 10 for your change. So I don't know if the intention here is kind of along those lines, like counting up to what their change would be, or if it's just to break down, like literally, given the currency set, given the currency set and what the cost was and what they tendered, here's the most logical, here's what you need to give them, right? If the change is, $63.22, I'm going to use US currency here because currency is just one of those things that's kind of like hardwired. It's difficult to think in other currencies. But, so then obviously that's 2 pennies, that's 2 quarters, a dime, and then, a 50 and a 10 and $2 bills, or, there could be varying combinations there, right? And you could get really complex. So I think that's what I'll do. I'll just, given the change that you're owed, I won't necessarily do the count up thing, but I'll break it down into the constituent parts. Like this is, if you'd never been a cashier in your life, right? If you'd never been a cashier in your life, this will tell you need to grab, 3 $5 bills, 1 $10 bill, 4 quarters, or 3 quarters, 1 dime, 2 pennies, that sort of thing. Okay, so here's the first issue. The first issue is we're dealing with money. And money is, you would assume that you could use double for money. And you can kinda. The problem is it depends on what you're doing. And the reality is, for like most financial calculations, floating point numbers are a problem. So we have float and we have a double, and these are, so it's important to understand that you can type decimal numbers in source code, and I think this is what confuses people. but they are not decimal data types. They are binary data types. They, and those binary data types are approximations of decimal numbers. That's why they're called floating point, because the way in which the binary representation is interpreted floats. And what that means is that there are certain numbers that cannot be represented accurately with floating point. The problem is a lot of those are numbers we would use for dollar amounts, for numerical money amounts. So you want to stay away from float and double for money. And this is true in C++, this is true in Java, this is true in C#. This is really true in any language that exposes floating point data types. Now, some languages have a more, like internally, they have a more advanced decimal package. And so for example, C# has a decimal type that's dedicated to this, and the way it doesn't float, their decimal type, it's like a floating point number in theory, but the way it's a larger number, it's 128 bits, and they burn a whole lot more memory and some computation time to make it stable, make it behave properly, up to, I think decimal can go to like 12 places or something, if I remember correctly. I'd have to look it up again. Java has a type called big decimal that's the same, right? It's internally, it's a scaled integer, and it supports bankers rounding. That's the other issue, is that the rounding behavior that you're going to get from floating point numbers again, it works great for scientific calculations, for 3D graphics, for things where if you're off by a few hundredths or something, or if you reach a number that, happens to end up being like the typical repeating decimal thing that happens with floating point numbers, it doesn't really much matter there. Yes, it's going to impact the simulation slightly, but typically it just doesn't matter from a pragmatic perspective. But with money, you can't have, you can't have an amount like 1.45 and then you add a thousandth or a 3,000ths to that, and then it jumps, right? Because you're using floating point and it can't quite represent that fractional amount the way that you have it entered. And obviously also, as the whole portion of the floating point number increases, the decimal amount, the accuracy there kind of fluctuates some. So anyway, we want to stay away from floating point. So how do we do it? Well, in the good old US of A, we have, let's see, how do I want to do it? Actually, well, yeah, let's do it that way. So what I'm going to do is I'm going to create a struct, and I'm going to call it US denomination P, and inside of here we're going to have a name, and we're going to have number of pennies. Because what we want to do, so find for your particular currency, find the lowest common denominator. In the case of the US, it's a penny. And then we can define all the units from the perspective of a penny. So this is an integer representation of of amounts. We'll go all the way up to $1. Well, actually, no, we'll go all the way up for all the different units of currency that we have. So this is our data structure that's going to map a name to our type. Now, before I go on, since I'm kind of doing this for beginners, I'll make some notes. We want to put this in a map, ultimately, a dictionary. Now, in some languages like Python or PHP or Perl or JavaScript, sorry, every time I say that, I kind of have a little reaction. You'd use a string or whatever, it doesn't really much matter, right? But keep in mind, for C and C++ programmers, strings are somewhat of an evil that you have to support, but you'll run into a lot of low-level folks that will say you should never index on strings or things, and that's kind of a reasonable position to take, right? Because why would you use a string where you could use a number? So, and of course, obviously an integer is going to be better. So let's do that. Let's create an enum class and let's call it US denomination type T. And so what do we have? We have a penny, we have a nickel, a dime, a quarter. We have 50-cent pieces, and we have, I'm going to skip some of the more esoteric. Nobody uses them. Nobody. We have $1. We do have a $2. We have a $5, $10, 20, 50, and 100. It used to be true, I think, many years ago, that we had higher units of currency. I think at one point we did have $500 and $1,000 bills, but to my knowledge, if we still have them, only banks have them. Nobody else uses them. So instead of putting the string here, what we're going to do is we're going to put the type on here. And the type, so now we have a structure that is, so especially if we do this, if we make our enumeration class, the base type is a byte, because we can fit all of our options into a byte, right? So this is a byte, this is 8, so this is a 9-byte structure, assuming there's no extra padding. Then the question is, okay, well, do we need a 32 or a 64-bit integer for this? It depends, right? I mean, I guess it all depends on what you're doing. Technically speaking, we could probably get away with a 4-byte integer here. I mean, that's a lot of pennies. That's 4 billion pennies. So if you divide that by 100, that's how many dollars that is. So, all right, but we want to get the name. We want to, how do we get a friendly name out of this? Well, the way that you would get a friendly name out of this is a 2-step process, right? So we can create an unordered map, and this will be US denomination type T to a string, and actually I don't need inline because it's not a header. And we'll say denomination names. Okay, so, oops, and it helps if I spell right. So I'm just gonna be really lazy here. No, do that. I'll do US denomination T. So I'm just going to copy that. This is not going to format right, but I'll fix it. There you go. All right. Now, there's a couple things to note. Because you'd want to think about this. Okay, so you're going to say penny or pennies, nickel or nickels, dime or dimes. Now, in some cases, pluralizing the words is easy. The cheater's way to fix that is to do something like this. If I can spell. Jeez. So then what we could do is change our map here. So it's a US denomination type T to a US denomination T. And then this in our map becomes a structure of this. So now we have a singular and the plural automatically. In some languages, like most Romance languages, these things probably pluralize fairly consistently, but English, that's not one of its stronger suits. So, I mean, again, there are like fancy libraries that will do a lot of this for you, but sometimes, you know, the easy solution is the better solution. And the nice thing about this approach is, that if we want to change, like if we want to say $100 bills, or, yeah, the funny thing is the singular and the plural here are always the same. Same thing. Like $50, we would never say that here. These would always be plural. But again, it doesn't really matter. We can hard code any combination we want for that. So that's how we would capture our singular and plural names. Now, we need a helper function that is going to give us back a US denomination name T. Now I'm going to make it a pointer because pointers are great to represent things that you can't find. I mean, yes, there are fancy C++y ways that you could do that. You could use standard optional and some other stuff, but you know, again, good old-fashioned, you know, C. Yeah, it could be. And again, like I said, we could change the names to anything we want. This is just a demonstration structurally of how I would go about doing it. So yeah, if you wanted to be really, really specific, you'd say $100 bill, because that's the thing you're thinking of, and $100 bills be $50 bill, the thing is, what's interesting is, while linguistically this is correct, nobody speaks this way. Nobody says $100 bills in practice, right? They say $100 or they say $100. But again, that's not that super important. So what we're going to do is we're going to make a static function called DenominationName, and we're going to pass in a US denomination type T. And we have a map here because there's enough options that we might as well use the map. So we're going to, from the map, we're going to find that type. If the iterator we get back is equal to the end iterator from the collection, that means we gave it a bad type. So we return null. Otherwise, we're going to return the address of the second part of the iterator, which is the value. The first part is the key. So now we have a map of types to descriptions in English. And you could imagine, right, if you had to localize, if you could have different, you could change the structure, right, where you could have different maps for different locales. There's all sorts of things that you could do. So this should give you an idea of direction you would go there. Now, we needed another map, because this is just our map for getting names, for getting descriptions of the types. So now we want to, let's move this guy down here. And keep in mind, I'm doing this all in a main CPP file. I'm not using headers. If you use headers, things start to change a little bit. And I'm doing everything above main so that it's pre-declared, so that when we go to use it, it'll just work. If you put stuff down here, you're going to have to pre-declare it above, or prototype it above your main function. So just keep that in mind. Okay, so now we need a map, and we're going to make this one an ordered map, because if we want to loop through it, right, to break things down, we're going to want to loop through it in order, or we're going to want to reverse it so we can go from high to low or low to high, whichever way we want to go, right? So we're going to make a map, and it's going to be US denomination type T, and this is going to be a US denomination T. And this is going to be S denominations. All right, so in this map, so yet again, I'm going to cheat because I was lazy. All right. So do we need to type in here? Because it's in the map. This is a tricky one. Like, sometimes it does make sense to denormalize and have the type, because you're going to get this back from the map. You may or may not have the key, again, depending on how you code it up. For this, I'm going to go ahead and just denormalize it. So, number of pennies is 100. Oops. So the penny is 1, nickel is 5, dime is 10, quarter is 25, dollars 100, 2, 5, 1,000, 2,000, 5,000, 10,000. Did I do that right? Okay, so there's our map of denominations by type to a structure that says, hey, this is what the type is and how many pennies are in there. So by the way, for those of you who are watching, I want to make another point here. If you're out there interviewing, I'll clip this section of this stream and I'll make it a separate video, but watch this. And again, this specific problem is probably not a problem you're going to get, but the process I'm going through here, where I'm thinking about the data types first. I'm thinking about what my data structures are. This is going to win you brownie points. Okay, this is what they want to see, all right? They don't want you to just run headlong into writing for loops and computation. I would, yeah. Domain-driven design is, okay, so I would call this data structure design or data-driven design. Now, I'm old school, so, but here's the thing about DDD. DDD implies object orientation. You have to be very careful. This is not domain-driven design. I am not puffing up a bunch of objects that have roles and yeah, we're not doing that here. This is just, to me, this is classic computer science-y type data-driven algorithm and data structure-driven design, right? Figure out what your data structure should look like based on the problem, and then write code, write an algorithm that handles the transformation from one state to another state, right? So anyway, there is a similarity in the sense that like domain-driven design would focus on the modeling first, but it's a different kind of modeling. Okay, so now we need a way to get a denomination. And I'm just going to go ahead and return a pointer. And I'm going to cheat. because it's lazy. See, this is the kind of what are you complaining about? Oh. This is the kind of boilerplate stuff that I'm hoping to eliminate with base code. You get the same thing, but you wouldn't have to do so much typing. Okay, so now, given a type, we have a way to get a denomination. Given a type, we have a way to get its descriptor, so we can pretty print it. And I would say, which one? This map, the denominations, or, so here's the thing, I haven't written the actual algorithm yet to do the change computation. So that we're gonna do that now. This is just setting the stage so that we have data structures that will make, the map is a definition of what our currency units are. So remember in your example, you had a for loop, a for loop, a for loop. You had all these variables and you had all these different loops. What I'm doing is I'm treating that as a data structure instead of treating it as code, which generally speaking is the approach you want to take. You want to try to first look at the problem as the data that you're trying to manipulate. And there are two types of data. There's reference data and there's instance data. And I hesitate to use the word instance because that gets people confused with classes and shit and objects, but the difference there is this is all reference data. I'm going to define this one time. These are facts, right? This is I'm going to reference this stuff. I'm not going to copy it. I'm not going to make arrays of it. I'm not going to duplicate it. I'm going to have another thing that I do when I'm actually computing the transaction, when I'm actually computing the change. That's the instance data that will use this reference data. So hopefully that makes sense. So, all right, so this is, like I say, we have the instance data. Now let's think about what we're gonna do, or I'm sorry, this is the reference. But let's think about what we're gonna do at runtime. What is the algorithm gonna do? Well, the algorithm is probably, we would like to have a US money T, all right? And inside of here, we're gonna have a field called pennies. But what we can do, so this is the first example where I'm gonna add some behavior. So our goal is to create an amount for, we need an amount for what the bill is, what the check balance is, what we have to pay. We want an amount for, so let's call this amount T. And I'm just gonna riff here a bit. So we want an amount T for the bill total. Actually, let's call it receipt total. And so obviously we could do this. So if we say the bill is $33, right, we could do it that way. And that would work. Now, I know Motorcade earlier told me, well, what if you want to get user input? Okay, what if you wanted to get a string? So here's where that is interesting. So first, you can't, well, there's two ways you could do this, I guess, to cheat. One, you could take the string and you could split it on the decimal and then parse this as an integer and parse that as an integer. And then you're going to have to compute the number of pennies, right? So this is easy. This is 33 pennies. And then this would be 102 times, 100, and you'd add that. So that's one way you could parse a string input, fairly trivially. Ultimately, what you'd probably want to do is build a little, either a regex, you could use regex, I guess, and get the zones and parse it that way, or you would want to just make a little state machine and parse it. So what the heck? Let's do that. But let's not do it that way. Let's make a static constructor that returns an amount t from amount. We'll use that as our example. All right, so this is right now going to return 0. That's no good. So let's make a little state machine. So we need whole, fractional. So we're going to loop, oops, I don't want to use a while. We're going to loop each character in the string that comes in. Now, some people are going to say, you shouldn't use a state machine, you should use regex, blah, blah, blah. I'm going to give you this example of how I would do it. Know that there are other ways you could parse the string, okay? However, I'm specifically avoiding streams. I'm avoiding scanf or fscanf. I'm avoiding, because all of those, if you try to scan that as a floating point, here's what's going to happen. It's going to load that, but that's going to be 102.333333333. It's going to repeat forever because a floating point cannot represent that number exactly. So we need to treat it zoned. We need to treat it as a decimal thing. Otherwise, you're going to have rounding problems. You're going to have computational. You get creep, right? As you do your financial, math, you're going to get pennies, like Superman 3, right? You're going to get these pennies that come from nowhere. That movie, that was the best part of that movie. The rest of it sucked. But anyway. So if the let's see, actually, how do I want to do this? Can't spell fractional. All right, so if is digit, then, so we need, again, we're doing a state machine here. So in fractional part is false. So if we get a digit, if in fractional part, then we're going to add the character to the fractional part. Otherwise, we're going to add it to the whole part. If it's a period, now we're in the fractional part. And we don't do anything with the period. Okay, so what's going to happen is we have a string that's an accumulator for the whole part. We have a string which is an accumulator for the fractional part. And we have a flag that tells us once we've crossed over to the fractional part. So we loop through the characters in the string. It comes in. We check, is it a digit? If it's a digit, then we check, are we in the fractional part? If we are, we add the character to that fractional part. Or if we're in the whole, we add it to the whole part. Once we hit the period, then we transition to the fractional part. Now, there's also, with parsers, right, it's never ending. What if there's a currency symbol in there, all this other stuff? For now, we're not going to worry about that. Those are cases you would probably have to handle in a complete solution. Okay, so now we have two numbers as strings, and now we can safely use one of the numeric conversion functions. So we can say A to L or A to I guess, and then we can cast it. Now these are older. I guess if I do the standard version, yeah, I'll do the standard version. So whole, we need to pass in the underlying pointer to it. And this is going to return whole amount, and then fractional amount, A to I. Oops. Okay. So pennies is equal to fractional amount. because those are pennies, right? And then pennies, we're going to add whole amount plus, now here's where we, you know, how 100% accurate do we want to be? Let's be pretty accurate. Although this is kind of silly, but oops. Let's look up a penny, right? Then we can say to penny, what are the number of pennies, right? And actually it's not, it's whole amount times, and it's not penny, it's dollar. There we go. That makes, well, I guess what I mean is that I'm building this around a US currency system, so I kind of know what the numbers are. But when I say accurate, do I want to refer back to my reference data? The answer is yes. I want to refer back to my reference data. So we look up a dollar, and because that's what the whole thing is. It's a count of dollars. So how many pennies are in a dollar? So we're going to add the whole amount times the number of pennies that are in a dollar. So this is the first example of where we look up our a denomination, and then we use that. So now the result here should be the number of pennies in the string that we pass in. So let's do this. I don't want to mess with importing libraries and stuff. All right. So we get 10233 pennies. So 10233 divided by 100 is 102.33. All right. So step number one complete. We can now create amounts from a string. And so now we have the receipt amount. We have the tendered amount. I'm going to scale these numbers down. Let's make this bill $12.67, and I'm going to pay with a 20, right? So let's say that this is receipt amount pennies, and let's say this is tendered amount pennies. Just make sure those come out right. And by the way, so people always talk about unit testing and all this. This is kind of, yes, I'm not using a unit testing framework. We could git catch and we could write unit tests and stuff. But to me, this is kind of the same thing. You write code, you have a driver program, you test things as you go, right? No, it's not test first. I'm such a shame in the programming field. Not writing my tests first. Okay, so now we have two amounts. So now people always, what's the difference between C and C++? Well, yeah, no regression. I know, I'm a failure, man. Just time to just give up. So, so what does C++ give you? Right? People ask this all the time. Why should I use C++? Well, I mean, this is an example of something that C++ can do that C cannot do, right? I can evolve this type. See, I like to call C++ type-oriented programming. The OO thing, I won't get into that, but I wonder when it was going to prompt me for the cast on those. So what C++ will let you do is, again, add behavior to types. Don't think of them as objects. Don't think of them as things that live in the real world. They don't. They live as long as your program runs. That's it. They're types. So in what way can we make the amount meaningful? Well, we can put a subtraction operator on it, because given one amount and another amount, we would like to be able to subtract. So let's return a new amount given our so the way this works is I'm overloading the subtract operator, and I'm overloading the one where we're given something on the right hand side, the left hand side is us, right? So this is the left hand, the right hand side is what's on the other side of subtract. And then I'm just creating a new amount, so it's very functional. I'm just creating a new amount. And I can't spell. Yeah, I know, that was a funny typo. And so I'm just doing the subtraction and creating a new amount. Now, obviously, if you do it, backwards, bad things are going to happen because this is unsigned. So, there's more in a full implementation, right? You would want to do some jousting to make sure that you've got it right. But we're going to assume the tendered amount is greater than the receipt amount. And so now let's add one more change amount. And the beauty here is, because everything's pennies, we're good to go, right? We just subtract pennies from pennies because it's the same unit. This is why having it all be at the lowest common denominator is good. All right. So let's test that. 1267, yes, 7.33 pennies, so $7.33. All right, so now, so far so good. I hope this is making sense. Now, while we're at it, let's go ahead and let's overload the add operator. And we can also we'll just stop here, because when we start getting into some of the others, then it's the question of, well, are you multiplying by amounts, or are you multiplying by fixed percentages, or what are you doing? But these are the simple cases, right? Adding and subtracting some money amounts. So now, okay. We want to get from an amount a sub unit of it, right? So, or I want to restate that. We want to say, given a denomination, how many of those are in the amount, right? So given a $5 bill, how many are in the change for this. Given a $1 bill, how many, given, you know, quarters, nickels, dimes, so on and so forth, right? So I'm going to use size T because for counts and things, that's kind of typically the standard there. Denominations present. So US denomination type T. So we need to look up that denomination. So we want to divide pennies by the number of pennies in that denomination. That should give us the count. So we know the change here is $7, right? So I should be able to say change amount, denominations present, $5. Ooh, that's a long one. And this is just a number. Right. So the number here should be 1, and it is. All right, so let's try another one. Number of dollar bills. Let's just do dollar. That should be 7. Ah, that's not good. Oh, because I'm... Beware of rape and paste programming. All right, perfect. Okay, so now, how do we... What's the algorithm to compute the change, the instructions, grab, because we want to use the largest to the smallest. Typically, that's the way you do it. So in this case, if I were doing this in my brain as a cashier, I would grab a $5 bill, a $1 bill. I would grab a 25-cent piece. I would grab it's 33 cents. So I grab a nickel, and then I grab 3 pennies. So we want to go from highest to lowest. So this is our denominations are ordered low to high. But I believe we're in luck because in an ordered map, yeah, we can do a reverse. Actually, we're going to do it though. Excuse me. Sorry. There we go. Okay, so we're going to walk our map And this is only true of an ordered map, right? So you have to make sure you use an ordered map in this case. We're going to walk from the highest to the lowest. Now, we also, before I forget, let's also implement an overload here that takes a penny count directly. Why? Because we're going to go through this loop and we're going to want to subtract. And then this one we're going to do in place. Yeah. All right. MATLAB, no. Python, here and there as needed, you know. It helps if I make it not constant. Duh. Okay. So, iterator should here have, oh, do I have to read it? Yeah. Okay. So we have to dereference the iterator here to get the key value pair. If you set to auto, it should adjust for you automatically. Okay, so the first is going to be the type. We don't care. Second is going to be the denomination. So what we want to do is we want to subtract, or no, that's not right. What am I doing? I want to get the amount in denomination. So we're going to call KVP second, which is our denomination. I'm sorry, that's not right. Change amount. Denomination's present. KVP first. Okay, so this is going to try to divide pennies by 100. Or no, I'm sorry, it's going to try to divide it by 10,000. That's going to yield 0. So what we want to do is we want to keep track of these. What do we want to keep track of? We want to keep track of the amount we picked, or the amount that was picked for each denomination. So yeah, this is where the, okay, so here's what we're going to do. We're going to create a vector of US denomination T. Remember I said about denormalizing that type and how that's going to be helpful? So we're going to have an array called denomination selection. And what's this? Helps if you include it. So we're going to get an amount in that denomination. If it's greater than 0, then we're going to in our denomination selection, we're going to push back a new US denomination T. So in this case, this struct actually ends up being both, I'm using it both as reference data and instance data because it's kind of the same thing. But not, right? This is actually a count. Yeah, so I need a different struct. All right, so let's do denomination selection T, or denomination count. That's better. So this is US denomination type T, and then we'll just use a 32-bit integer here for the count. All right. So this is going to be denomination count T, and we'll call this denomination counts. We'll just call it count. And that size T so it matches. All right, so we're going to loop backwards from high, or however you want to look at it. We're going to loop from the high denomination amount to the lowest denomination amount. And we're going to ask the change amount, hey, given this denomination, how many denominations are present of this type? We get back a count. If it's greater than 0, that's a bill we can take, right? So we're gonna, a bunch of these are gonna be nothings, right? Nothing, 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 until we get here. We're gonna have, we're gonna have 1. Then we're gonna subtract as we go along. So we're going to reduce the change amount. So then we're going to get, it's going to be 1 of these, 2 of these, 1 of these, no dimes, 1 nickel, 3 pennies. Right? That's what we should get. So change amount minus equal. And then this is where we say KVP's second number of pennies, right? Because we're going to take, is that what I want? Someone tells me, no, that's not what I want. Actually want count times and that should be fine. What is this? No, I didn't do. Yeah, I got it. All right. I didn't do negative assignment. That's a different overload, but right. So we're going to take So I should just be able to do that. Yeah. All right. And that's in place, so that kind of looks funky, but it's correct. So yeah. All right. So then, just for test here, let's that's kind of funny. So I'm going to set the debugger so we can walk. So we're going to get the count, which is going to be 0, right? Ooh. What did I do? Oh. That is one very unintuitive thing about iterators. All right, so this should be $100. This should be 50, which is 0. This should be 20, which is 0. 10. 5. There we go. We got our 1. Now we're subtracting that. There is a $2 bill. So it finds a $2. All right. So now, what are we getting here? Oh, there are no $1, right? Because we got a $2. There's a quarter. Right, 1 quarter. Dime, there are no dimes. There's 1 nickel. And there's 3 pennies. All right, there you go. Ooh, huh? Oh, my bad. I forgot. I was all fancy and stuff. So let's be fancy. So let's do this, not count. So if denom count is equal to 1, then or no, denom count. And then we're going to do DenominationName singular. Otherwise, else. Plural. And let's switch the order here. So it's going to be the number space And there's the solution. You're going to give them one $5 bill, a $2 bill, 1 quarter, 1 nickel, and 3 pennies. Now, that was fun. That took me an hour and a half. So, all right, we can get rid of our debug output. Now, here are some interesting edge cases to this problem, right? $2, yes, technically we have in the US a $2 bill, and they're semi-prevalent. But they're not super prevalent. And you might want to have something on there that says, okay, I'm gonna skip that because it's not all that prevalent. So then you could get really fancy, right, with something like this. Right, exactly. So what you really, to like completely do this problem justice, I think what you would have to do is you'd have to have the concept of a cash drawer. And you'd have to, in the cash drawer, you'd want to put how much of each unit you have. Then what you would do here is you would check against your cash drawer, and if you don't have that unit, you would skip it and go to the next lowest unit. So if you're out of 20s, you'd go to 10s. If you're out of 10s, you'd go to 5s. That's because that's what happens in reality. And if you don't, even though the math might work, like a $2 bill is a valid selection, you may not have a $2 bill. So then what, we'd get the count here, we'd say, okay, we'd ask the cash drawer, do you have this number of this denomination? The cash drawer would say yes or no. So yeah, so there you go. Not too bad. So what I'll do is later today, I will put this code on GitHub, and I'll post a link on Discord and Twitter for people who want to take a look at it. And like I said, I'll clip this part of or highlight this part of the stream, and I'll put it on YouTube, and I'll put links to that too for folks who want to follow it. But yeah, I mean, there's all sorts of stuff, right, that you can do with this. This is, again, this was a request from a viewer, and they were specifically, this was kind of to the point where their solution stopped. But yeah, if you wanted to go all in on this problem space, we'd want to model a cash drawer, we'd want to populate it, we'd want to have the ability to set up rules, right? Like, we don't accept bills over a certain size, right? So your tendered amount, we could investigate like what combination of bills were actually tendered. Do we accept that or not? Then when we're making change, do we actually have change? Of course, then you can get real crazy, right? Because what happens in real life is if you don't have enough currency in the till, so to speak, to make change, you have to then escalate it to management, and then they buy, you buy currency from them, right? So that you take the high denomination bills that you've received, like you maybe have a bunch of 20s, right? And you take those, and then they break it back down again into a set of acceptable currencies. So, but see, here's the thing, Keith. I mean, I agree, unit tests can, but this is the part, again, unit testing, as it was originally conceived by the XP folks, the people who brought it to the forefront, it is not about testing, it's about design. But I can do this design without unit tests, right? I don't have to go to a file, start writing code, say, the compiler say, oh, I can't compile that, then go, I don't have to do that, right? I'm sorry, that process to me, like TDD is meaningless. Sure, if you're an absolute beginner, maybe it can help you think through some stuff, maybe. But I would argue too, having just a little test program where you can kind of plod through it can help you think through things too. So, and then the concept of actually testing and test coverage, that's a separate thing, right? So it's not, one's a design concept, one is something else. But yes, I will definitely put this up on GitHub and I'll clip it. That was fun. And so if others have similar, problems like that you would like me to work through, I would be happy to do that.